So welcome everyone to the fourth day of our workshop, and it is the last day when we meet through the Zoom. And you can see also those who joined a bit earlier, there is a message in the chat that today also at 6 o'clock we'll have one more meeting where we'll have a presentation given by Franz von Silva-Taroca, Vice President of Push Quantum. So I definitely recommend you to attend, and it will be after 4 hours. So I hope everybody more or less used to the time shift if your country experienced it. So today we'll speak about the Grover search, but before then, let me know if you have any questions about what we did so far, or maybe some technical, organizational questions, homeworks, and possibly some other stuff. All right. Good afternoon, you too. So basically, today our plan is similar to previous days when we first go through notebooks, and after that I will launch the last final quiz. As usually, it is just intended for fun. And today we have just 3 notebooks to cover, but it might be quite intense. It is about Grover search, but I will need to give you some extra information in order for you to be prepared. So what we learned so far, most of the things will be used. So there is one more thing to learn. So first, the thing is, does anybody know what is this show? Does anybody know what is the name of this show? So who of you knows this show? Please let me know. Whether there is at least. Okay, good. So we have people who is familiar with the show. Those who don't know, it's called Sesame Street. So you can see that there are different Muppets, and so yeah, there are several different characters. And today I promise that we will work with Grover search. And what I discovered, one character, this one, he's called Grover. So Grover is very useful when there are resource intense tasks. I mean, look, he provided resources for one of the people, and overall, Grover search algorithm indeed can solve some of resource intense tasks. So I introduced you Grover, and now your task is to please find Grover. Please name the row and column in this image where you can find Grover. So I see proposals that solution is row number 4 and column number 3. And you're right, so indeed, this is where the Grover is located. So congratulations, I managed to teach you Grover search in 2 minutes. So now you learn how to find Grover. Okay, so this is introductory joke, which I sometimes use in the workshops. And the thing is that what kind of search we'll actually be doing and what kind of tasks are we solving. And actually, yeah, I managed to save you a lot of time for this weekend. But basically, the tasks for which Grover search is intended actually has some similarities to what I have shown you so far. So you see that now we have some 16 elements, and we needed to check one by one until we find the right one that we were looking for. So we were looking for image of Grover, and we found him on the bottom, on the third column. So basically, it is a task called unordered search, because you didn't know in advance what is the order. So whether it is alphabetical or maybe by colors, there is just some order that you don't know. So for us, it is unordered array of information. And then you need to check them, and then you realize when you find the entry that you were looking for. So let me share now the regular browser screen, and also I will turn off now the camera for those who might need to save traffic. So now suppose that we have array of data. First example will be like boxes, which will be very similar to what we have seen so far. So suppose that we have 4 boxes, and in one of them there is something that is hidden. For example, here we have like golden star hidden, and other boxes are empty. Our task is to find then where this golden item is hidden. And so if we don't know any principle how it is located, then for us, it is just a matter of checking each box until we find. So we check this one, we get answer, no, it is not here. We check this one, we get okay, this one is also empty. And here, okay, this one is containing the element that we were looking for. And we can think of our boxes being some indexed like this one. So we have state 0, 0, 0, 1, 1, 0, and 1, 1, like being numbers of this. So yeah, this is how it may look, our situation. So we have enumerated elements. We're looking for some element with some property, for example, that it contains some element. And then we check one by one. Classically, we probably would do in this way. I see the question about nonlinear quantum systems. Maybe somebody who is participating has been looking in this direction, because Sadelight didn't. Like how it can look like if we have nonlinear quantum systems. I know for sure that about irreversible cases there are researches, but actually it has also some physical explanations, like why we do measurement and we lose reversibility, for example. But about nonlinear systems, so if anyone, because I'm sadly unaware about how it is going, research on nonlinear quantum systems. So meanwhile, I will continue with Grover search. So this is kind of search that we're performing. So we have some elements, one of them has some property, and we would like to find the element with this property. In our case, these are boxes which are closed, and we need to open them one by one to realize whether the box contains the elements that we were looking for. Another example could be, and by the way, it is not coincidence that I'm putting also indices here. So suppose that you have a phone book, where again, you can access entries by their indices. So for example, we have 5 entries in our phone book. And so in phone book, we have some names. For example, we have name A, we have name B, we have name C. And for example, we have here a test man. And last one, let it be K. So we have a phone book, and it doesn't have any specific order. So names are not ordered. We just have entries which appeared one by one. And here, for example, we have a phone numbers. So suppose that we have now this database and we would like to find a test man. So this is again element with some number. In our example, it's number 011 or 3 in decimal. And we want to find test man to see what is his phone number. It's 615 in this example. So again, classically, we would just check elements one by one until we find the right one. After that, so from our search outcome, we would get index of elements stored in our database that corresponds to the test man. And what remains to do? We can just access now this element by index. So we see indeed it is test man. So our search result is correct. And then we can just read out the information that phone number is 615. So these are kinds of search that we will be doing. We're finding some item with some property. And now let's see how do we work out on search task in a bit different way. So these three notebooks, the last ones, and all of them are in final section. And this time order will be exactly the one that they are placed. So I will prepare you by these notebooks to how do we implement Grover search quantumly. So we will give explanations through a simple game to give some ideas about the principles of Grover search algorithm. So suppose we have a list of n elements, like my example with boxes. Some of them are marked. Marked element is the one that has properties that we're looking for. At the beginning, each has value 1. So you can think of them in quantum case as their amplitudes. Currently, let's think that it is something that affects our probability to find this element. So each iteration of the game has 2 phases. So we will have repeated phases, and each phase consists of these 2 operations. First one is query. In this, we assume that each marked element is detected and its sign is flipped. So like its value is multiplied by -1. And second is inversion. In this phase, the value of each element is reflected over the mean of all values. Mean means average of all values. So here is a task to implement it. So in first cell, you can see that indeed we have list of 8 elements. So here we have elements, each element has value 1, and we have labels 1, 2, 3, 4, 5, 6, 7, 8. And here your task is to implement the operations. First one is query phase, where you need to change sign of the marked elements, which means multiplied by -1. And in this task, we have 8 elements and only element number 4 is marked. So then you would need to keep all elements with same value, but multiply element number 4 by -1. And in second step, you would need to do inversion about the mean, about the average value. What you need to do, you need to first calculate the average of all values and then reflect. How reflection happens, here you can see. If we have mean value 0, then reflection of 3 will be -3. So you can think of it as you have some graph, and let me show you on solution images. I will not stop on the code because this is a task that you would need to do after the lecture, but I will show you how the outcome should look like. So this is that we have all elements with value 1. After that, we need to multiply, because we do query, element number 4 by -1. And this is what happens. So all of them have value 1, and this fourth element has value -1. And now we would need to do inversion about average value. This, sorry, I a bit misclicked. This would be the average value. How we calculate the average value? We just do summation of all elements and divide by the number of elements. So we have 7 elements with value 1 and 1 element with value -1, so 6 in total. Divide by 8 and you got 0.75. Now the question is, how do we calculate the new values? So basically what you need to calculate this difference between final value and average value. So here I show you 2 different cases. And then you need to reflect it to the opposite side. So this one would go here, and this one would go here by the same distance. So it looks like reflection that we're used to. And in some sense, it is a reflection. So usually people struggle of how to calculate it. So you have average value, let's denote it by letter A. And you're calculating for some element, suppose this one, let's call it X. So we have average, we have X. Now we calculate difference. So let's denote it by letter D, and difference is equal to X minus average. This is our difference. So we see in our example for the first one, it is 0.25. And now what we need to do, in order to find the new value, let's denote it by X with some additional prime symbol. It will be equal to average minus the difference, because we want this difference to appear on the opposite side. This is why we take A minus D. And so this is the way how we calculate the new value. So now let's see how it looks. And this is what we get. We see that for all elements, value became smaller, but for marked element number 4, value became bigger. And this is basically what Grover search does. So you can see that now if we would apply this one iteration, we would find element number 4 with much higher probability than all others, compared to initial case when all of them would be found with equal probability. Then we need to repeat this process. So again, we multiply it by -1. And now we again do this inversion. Not quite, it's 2 times the difference if you consider the first element that you had. So basically, Notepad online. So as I have shown, you have average value, and then you have difference is equal to X minus average, and a new value of X will be average minus X for each X. And so you can also, sorry, not X, but difference. So average minus the difference. So then your difference appears on the opposite side. So it's, yes, it is like X minus 2 times difference, but you need to calculate this difference through average. And actually there is one more smooth way how to do it. It can be just average minus X minus average. So now you see each X new is only dependent on the average value and X value. If you open up the brackets, you can see it's quite unexpected conclusion that it is 2 times average minus X. This is how we calculate new value. Yes, you're welcome. We first did workshops on site, and this was the part where roughly half of participants, or even more, were not sure how to calculate it. So I gave usually at upcoming workshops explanation like this. So yes, this is how the Grover search behaves. So you can play around with this task. In task 2, now you're asked to write these functions that do query and inversion in order to make them in a loop. So you don't need to copy paste the code. You can just write it for a different number of iterations. What we do, we will repeat the same game. So we have 8 elements. Elements number 4 is marked. And now we use 20 steps. So 20 iterations, each of them is query and inversion. And now we will trace values only of the marked element to see how all this algorithm would affect our marked element. So we will store values of fourth element after each step. So after each query plus inversion. And this is what you're asked to do in task 2. So how do query works with of elements, how inversion affects all elements. So some similar code to what we do in task 1. And then you would need to apply the iterations. If we use undefined code, let's see. So here, since we didn't change anything, we have no change. So if you would implement inversion and query, then definitely this result would change. Let me show you just how it would look like. Basically, this is what you get. And you can see that we started with value 1, then we get 2.5, then we get even bigger value, and then it becomes lower and even negative. Then it reaches some peak at the bottom, then again goes top, some peak at the top, and so on. So you see some very strange behavior. If you do classically the search task, the more you check, the higher the probability to find the element. But as we see how the Grover search behaves, we see that probability is not always growing. So there are some peaks, and we would be interested to exactly stop our algorithm at peak so that we have the highest possible probability to observe our element. And this is one of the differences between quantum Grover search and classical approach to search problem. And here are several tasks where you need to repeat it with different number of marked elements or also for different number of elements in total. So we have seen two operations basically that govern our Grover search. We have inversion about average value, and we have query where we multiply by -1 amplitude of marked elements that we're looking for. And next tasks are to show us that actually these all operations are length preserving, so therefore they are valid quantum operators. And later we will learn how actually to implement them. So let's see. Now we are asked to print the length of list of elements. And length again is square root of the summation of squares. And what we see that if we have 16 elements, we have square root of 16, so initial length is 4. And when you do task 5, you will see that at each step in the iterations, you'll have always the same length of the vector. And as we remember, each length preserving operator is valid quantum operator. I'm not sure, I guess it was here. Quantum states and quantum operators. Any length preserving square matrix is quantum operator. And this is our case as well. So as observed, as you will see in the tasks, that each phase of the game is length preserving operator. So whether we can represent them in form of matrix, and we see that answer for query operator is easy because indeed it changed sign only of marked elements, and so it will be identity matrix having -1 in some of the diagonal entries. For the second operator, it is not so obvious in the beginning, so this is what we'll observe a bit later. So now we try to represent list as a valid quantum state. So if we have 8 elements, all of them have same amplitudes, and summation of squares should be equal to 1, so that it represents valid quantum state. What should be the amplitude of each state? This is what is asked here. So I will write this question also in the chat. So this is the question from task 7. So please think a bit. Okay, we have one proposal. 1 divided by square root of 8. Are there any other proposals? Or maybe somebody also agrees that it should be 1 divided by square root of 8. So let's see, if we have 1 divided by square root of 8, what do we get? We have 8 elements, so summation will be equal to 8 multiplied by squares of this value. So 1 divided by square root of 8. It is amplitude for each element. We take it squared, and we sum all them together, which means multiply by 8. And what we'll get 8 divided by 8. which is exactly equal to 1. So, thank you. Indeed, your answer is correct. So now we implement this same game, but this time we use valid quantum state. So now, indeed, our game is representing a quantum state. And let me check. So yeah, here we see that each of them will have 1 divided by square root of 8, which is the same as 1 divided by 2 square root of 2. And here we'll see that after each step, we'll have summation of squares equal to 1. So if this would be a quantum state with some amplitudes, and we would perform Grover search, then it turns out that we will always have the valid quantum state. So all these operations are valid quantum operations. And so here will be some information. So modified game, where we now have amplitudes that represent real quantum state. This was a modified game, which is part of the Grover search algorithm. So this like making you more familiar with principles of the algorithm. So we are given some unordered list, and we make search of a specific element that is called marked. We access a list via Oracle, to which we can make queries to the list. If we have n elements, we can use log n qubits, because we can represent 8 states, 8 elements with 3 qubits. So you see how it scales. So this is why we have logarithmical number of qubits. For 2 to the n elements, we need just n qubits. And our basis states will correspond to the index in the list. So what we have seen here, now we would have like quantum states would correspond to the same index. So if the search element is detected, then Oracle operation will flip the sign of the amplitude, so multiply by -1. Keep in mind that here we simulated Oracle with pre-knowledge of marked elements. So currently, we show you how it would work like if we have access to Oracle, which already knows which element we are looking for, which one is marked. In real implementation, Oracle should have quantum mechanics that are detecting the marked elements while being in superposition of all indices. So matrix would look as discussed. It will have just value -1 for the marked element. And so the signs of corresponding amplitudes would be flipped automatically. The thing is that this is the main technological challenge for implementing Grover search algorithm. So we have all the theory, but for practical purposes, at least for general solution, there are still some difficulties. For specific cases, we can design oracles indeed. And here will be some information very soon. We start with all qubits having the same amplitudes, which means that at the beginning, Hadamard operator is applied to each qubit. And so amplitude of each basis state is set to 1 divided by square root of n. By the way, if we have all states with same amplitude and we would do the measurement at the very beginning, so we just applied Hadamard and then we do the measurement, we would get each of the states with the same probability. So you see, then we get exactly probabilistic outcome. But because we can improve our amplitudes later, then our measurement outcomes will be better. So this means that we applied Hadamard. It is the same as if all elements start the game with the same amplitude. After that, game starts to iterate, and so amplitudes of marked and unmarked elements are changed. How many iterations do we need? This will be answered in next notebook. But usually, if number of marked elements are less than unmarked elements, amplitudes usually start to increase. After that, we reach first peak, such that the probability of observing marked element takes its maximum value. After this point, amplitudes start to decrease. So we need to stop iterations at the moment when we have maximum amplitude. And in next notebook, we'll have answer. how many we need. Operator in each phase is unitary, and unitary matrix of the query phase depends on the input, but unitary operator of the inversion does not depend on the input. So in the query phase, amplitudes of marked elements change sign. But in inversion phase, we see that for each value x, new value is calculated as 2 times average value minus x. And interestingly, it can be explained in this way through matrices. So we have vector of size n. And so we have the following row vector representing vector of same amplitudes. And we consider all elements in the list. We work with the following matrix. So this represents mean value 1 divided by n. So this would be a matrix corresponding to mean. And you see, we have 2 multiplied by mean minus identity. So this is a matrix that corresponds to our inversion phase. And here 2 tasks just to convince yourself that mathematically indeed it performs what we are expecting. So that this operator is exactly providing us these changes to the amplitudes. And now the general form of the Grover search. So suppose that we have big N number of elements in a list L, and one of elements is marked. So we can define the property whether element is marked or not as some function f, which accepts x as an argument. So we pass to it x being our index of elements that we are asking for. And function will have value 1 if element is marked and 0 if it is not marked. So in more general sense, our algorithm can be defined that for some given function f, Grover search finds element x such that f of x is equal to 1. So how does it correspond to finding the marked element? Sadly, I deleted example with boxes, so I'll draw it again here. And here we had some shiny golden object. This time it will be sun. Thermal synthesis, for example, that we are all searching for. And so these were our indices. And we can think of f being a function of opening our boxes. So f from 0, 0, our box is empty. So it will be equal to 0. And this box contains our shiny golden object. So f from 1, 0 will be equal to 1. So this is how we can look at it, at this function f. So we can access the list by querying this function f, and such function usually is called oracle. In the worst case, you would have to query all possible inputs until you find the x that satisfies it. So if it was the last element and you check them in specific order 1 by 1, then it might be the last element. So how many times do we do this query to the oracle f is our query complexity. So we can think of like how many operations we perform to check the boxes. Checking each box takes 1 operation, so we need to check n boxes in worst case. And this is our query complexity. O of n means that it is like linearly proportional to number n multiplied by some constant. In our case, it is just n. Grover's algorithm is able to perform the task with square root of n queries. So this is where we get improvement. Here is a remark that please check the big O notation if you see it for the first time. So here we assume that we have only 1 element that is marked for simplicity, but Grover search also works if we have more than 1 marked element. But basically here you can see that we'll have quadratic improvement on the square root of n queries are needed in Grover search. So here will be one more example. Not quite, because Oracle means you should query the database. So if we have just Oracle and we see its internal structure, then in some sense, yes, we will have an answer. But in general, we have access to Oracle, to which we can ask questions. So it is like with database. In some sense, you have database, it have million records, and you can say that we have already answer. But still, we need to search through it. So we need to check it one by one. So in this sense, still, it doesn't mean that we have it right in our head. Yes, Grover's search algorithm is challenge to real quantum computer because we will do search in superposition. And so here we'll access Oracle in superposition. So like classically, as you have seen, we are checking elements one by one. Quantumly, we do it in superposition. And this superposition was represented like this. So with our amplitudes, we are asking for the elements, and then our amplitudes are changed in the process because of the query phase. So when we found it, you did the measurement, you found it, and yes, it will collapse. And with high probability, it will collapse to the state corresponding to the marked element. This is basically what we are doing this search for. So Grover search can also be applied to something more general, not just a list. So as long as we can construct such function, we can search in some specific settings. So suppose that here we have picture, we have 4 cities, A, B, C, D, and we have distances between them. So here you can see 100, 200, 300, 400. So if we start in city A, does there exist a path of distance less than 900, which will visit all cities exactly once and will return back to city A? It is decision question of trailing salesperson problem. So the search space consists of all possible roads. So there are many of them. You can see we have like all different orders of A, B, C, and D. And we want to find the roads that's total distance is less than 900. If we have A, B, C, D, A, then we'll have exactly 800. So this would satisfy our condition. For all other roads, it will be more than 800. So this is example of function to which we pass a road, A, B, C, D, A. Answer will be 1 because it is less than 900. For all others, it will be 0 because it is 900 or more. How we can construct such function? We can add distances between each pair of cities and output 1 only if it is less than 900 and f is equal to 0 otherwise. So as you can see, to implement function f, we do not need to know the solution. So this is example where we build Oracle without knowing the solution. So we just define the function. So we would need to define and implement it quantumly in order for it to work. But keep in mind that in general, it is not always an easy task. Yes, it is possible to have more than one solution. Until this moment, we were looking at examples where we have only one solution to simplify things. But actually, already in this notebook, there are tasks where you have more than one solution. So in short answer is yes, and we will see it in upcoming notebook as well. So how the Grover search would help if we have such function? Checking all roads one by one can take long time, but if we have a road, you can easily check the distance that satisfies the condition. So instead of checking all roads by one, we would need just to do square root of queries because we have quantum approach to do them in superposition, and so Grover search would lower number of these queries. So if you want to see more examples, you can check the link here. But basically, yes, this is like to show you that there are another less abstract examples. So before it, we had abstract example where we have marked element, and here you can see example how it behaved. But in general, we can have just some function to which we pass values of parameters, which could be our indices of elements that we're looking for. And we could get answer 0 or 1. Any other questions? It is totally fine that you would need to go through these materials once more because it is a lot of information. Currently, if you understood the idea with query and inversion through the graphs with amplitudes changing, this is already very good. And another thing is about the number of these iterations is better than in classical case. We have square root of n instead of n. All right, let's then continue. Now will be more analysis about the behavior of Grover search. The execution of Grover search algorithm can be simulated on a unit circle. So idea is a bit similar to what we have observed here when we traced only amplitudes of marked element. This time it will be from a bit different perspective. So amplitudes of marked and unmarked elements never differ from each other. Therefore, we can group the elements as marked and unmarked elements. So maybe let me show you one more task where we had multiple marked elements to explain what does it mean. So somewhere we had for multiple marked elements. Okay, probably we will not. Okay, we'll see. So at the beginning, all states have the same amplitudes. And after that, here we see the first 12 are marked, other 4 are unmarked. And you can see that they always, among them, share the same amplitude. So each marked element has same amplitude, and same case for unmarked elements. Each unmarked element will have same amplitude. And it is always the case. Here you can see example where we had only one marked element. It has some amplitude. All unmarked elements share among them some other amplitude. So this means that we have just two cases of elements, marked and unmarked, and they will have corresponding amplitude. So we group them together. This would simplify the analysis. So length of list is 1, so we can represent the list as unit vector on the unit circle, so like we did for a single qubit. And we'll have y-axis, which was state 1 in our 1 qubit representation in the past. It will represent marked elements, and state 0, x-axis, will represent unmarked elements. So this is the idea how it would look like. This is just example. But by the way, this is example where we have 8 elements in total, and one of them is marked. As you can see, if we would have such state and we would do the measurement, then of course, high probability to get unmarked element. So this is nice thing about this visualization is that it gives us information about what would be the probability to observe one of the marked or one of the unmarked elements, which can simplify things significantly. So here we have example with 8 elements where we have 3 of them being marked. 3rd, 4th, and 7th. So we remember that Grover search starts in equal superposition, where we apply Hadamard to each qubit. This is how it looks. So basically we have amplitude 1 divided by square root of 8 for all 8 basis states. And now we try to group them. You see here. U is equal to 1 divided by 2 square root of 2, where we have 5 unmarked elements. And here we have 3 marked elements. As vectors, it would look like this. So the question is, how do we represent such state on a unit circle? So first of all, x and y axes are orthogonal, and same is for marked and unmarked elements. So therefore, we can represent our vector like this. And we need to normalize our vectors. And this is basically what we get. So we get the amplitude for unmarked equal to square root of number of unmarked elements divided by square root of 8. And for marked, we'll get square root of 3 because we have 3 marked elements. And so this is our representation then on a unit circle. We'll have for unmarked, which is amplitude of state 0, we'll have square root of 5 divided by 2 square root of 2. In other words, 5 divided by 8, and we take square root of it. And for marked, we'll have 3 divided by 8. After each phase of Grover search, as we have seen, entries of marked and unmarked do not change. Here are some ideas, but overall, during the Grover search, we'll have the following correspondence. So we'll have 2 additional numbers, a and b, that would multiply as the amplitudes of marked and unmarked elements. And for marked and unmarked, we have noticed that we have n minus k for unmarked, and k is the number of marked elements. So you see, we already are speaking about cases where we have more than one marked element potentially. So here we need to visualize Grover search when we have 5 repetitions of our algorithm. Here we won't have anything interesting only because it is unfinished task. So this is that you would need to play around with different examples, with different number of elements, different number of repetitions. And you visually would need to understand when your vector is pointing closer to the marked, on the top or on the bottom as well, it works fine, but better on the top. So to determine how many repetitions was optimal, so now finally the analysis. Idea behind Grover search algorithm is that amplitudes of marked elements can be quickly amplified, and so the probability of observing one of the marked elements will quickly approach 1. For quick application, we need to apply 2 reflections to our quantum states. So the first reflection is clockwise rotation, the second one means counterclockwise rotation. And both reflections will give us rotation by 2 theta, where theta is angle between initial state and state 0 on the unit circle. So here is the visualization. We start in state of equal superposition, which will be this yellow line. So here we see, we'll start in the following state. The first step is multiplying of amplitudes for marked elements by -1. You see that we have marked being vertical one. So basically, it would be a reflection, the one similar to what we have observed before. You remember there exists a reflection over x-axis. So for state 1, amplitude was multiplied by -1. This is exactly the case here. So after the query phase, this is our new vector that we obtain. The second one is trickier because the second reflection is actually over the axis of initial state. And so now you see, we started in this state. After one iteration, we now are in this state, U2. If we repeat it once more, you see again, we reflected to the bottom through unmarked axis. And then we reflect once more through this yellow line. Now you see we are even closer to marked state. So you can see that actually we're doing rotations. So in the explanation before, we have some angle theta. So this is our angle theta. And each iteration is giving us rotation by 2 theta. This is geometrical property that you can check in your spare time, that 2 reflections give us 1 rotation by twice the angle between these reflection lines. But basically, you see, in this analysis, our vector will be always rotating by 2 theta. And we need to stop when we are close to this place. And this is what it will be about here. So when to stop? We should be careful when to stop, because after hitting maximum values, amplitudes will quickly decrease, and after hitting minimum values, they will again increase, and so on. If we have trivial example and consider rotation unit circle with angle pi divided by 8 and start in 0, every 4 rotations will visit first state 1, then -0, -1, state 0, and so on. And so when rotating, our probability will oscillate between 0 and 1. And so this is the number of iterations. It can be proved. Currently, just keep in mind that this is the optimal number of rotations. So if we have one marked element and we have list of size n, then we need pi divided by 4 times square root of n number of iterations. So this is where we get this square root of n. And after this number of iterations, probability to find the marked element will be very high. If we have more marked elements, then we just need to lower number of iterations, we divide it by square root of k. Because you can see if we have more marked elements, this yellow line will be higher, and therefore this angle theta of rotation will be also bigger, so we need fewer number of rotations to reach state 1. And if we don't know how many marked elements we have, we can actually iterate experiments by thinking first if there is 1, then thinking that there are 2, then 4. And when our k will be close to one of these cases, then in one of these experiments, we'll get marked element with high enough probability. So therefore, total number of iterations still is proportional to square root of n. Okay, so first question, where the 4 rotations rule come from? This is just example here. We have pi divided by 8, our rotation angle. So then in such case, if we start here, we'll do pi divided by 4 rotations, pi divided by 8. Then you will get to the top like here. Marked elements is one that we are searching for. So we denote it as element with specific properties that we're looking for. This is like checking the boxes. We do not know what element is marked. Here we see just how the Grover search behaves if we have access to the oracle this is how our amplitudes would evolve. So of course, all these demonstrations are shown, like what if we would know in advance which element is marked to see how it evolves, how it behaves, to see that it actually works, but only if we have access to the oracle which affects marked and unmarked elements. This is a good question, actually, because like we cannot mark them. The oracle is marking them. Like say part of the nature of the oracle. So here we just analyzed if we do queries to such oracle, then this is how it behaves. And of course here it seems like if we already know what is marked element. But even if we didn't know what is marked element, this is how it would evolve. This is why stated here that if we know number of marked elements, we know ideal number of iterations. If we do not know how many of them are marked, we still can implement these experiments, so Grover search for different number of iterations, and we will still find it with high probability. So the question that was put aside is, how do we implement oracle? And this is a challenge. All other operators are implementable quantum, and this is what we will see in next notebook. Another remark is, you have noticed here we had some example of function. We have one more course called Nickel, which is not quite a continuation to this, but it more focuses on oracles for the Grover search. So I highly recommend you, whenever Nickel will be organized, to attend it, because it will also answer some of your additional questions exactly about oracles. And basically there we would observe how even we can implement oracles for specific problems. And so maybe in future, we'll have some hardware solutions for general cases as well. Yes, number of iterations, indeed, it is some rule, let's say, and it was derived through analysis. So because we know the rotation angle, we know how many rotations we need to perform to get to the state which is marked with high probability. So yeah, basically this is a number of iterations that you should always perform for Grover search. This part is optional just to verify why reflection over the mean, this second step, is always reflection over this yellow line, which represented our initial state. This is optional. You can see here is a bit more than one page of text, but those who like mathematics, I recommend you to check it. Please let me know if you have more questions, because after that I will announce a short break and we will see the last notebook where we put together the knowledge to implement the Grover search. So to program it. Thank you very much. If you are leaving, please consider to check the recording later, because we'll have one more notebook. Okay, so I guess it's time then to announce the break, and this time it will be 8 minutes long. We have 8. Now, so we continue at 15:15. So see you very soon. And if you will have more questions, feel free to write them and we'll react on them when I'm back. See you very soon after 8 minutes. Let's continue. I had small snack, so maybe my voice will be a bit delayed for a while. Basically, we have just one more notebook left, and I didn't see new questions. Let me see also if microphone, I think it works properly. So this is 92, Grover search, the implementation. We'll consider how to implement Grover search. And here we recall first the whole algorithm. So we consider the case when we have one marked element. If we have more marked elements, we'll just have different oracle. So we are given 2 to the n elements. One of them is marked. Task is to find the marked element. We'll use n qubits to search among 2 to the n elements. At the beginning, we will apply Hadamard to each qubit so that we will put our quantum state into equal superposition. So we have all basis states from 0, 0 to 1, 1, and their amplitudes will be set to 1 divided by square root of n. And then we iterate the following algorithm for several times. We do a query. So we apply query oracle operator to qubits, and it will flip sign of the amplitude of state that corresponds to the marked element. And inversion. It is also called a diffusion matrix. So amplitude of each state will be reflected over the average, which is mean of all amplitudes. So if we write down as a circuit, then we have the following circuit. So we start with all qubits in state 0. This is how it usually is initialized in a quantum computer and on local simulator as well. After that, we apply Hadamard to each qubit. And then we iterate query. So when we use our oracle, and then diffusion, we repeat these operations for some number of iterations. So square root of n, as we discussed so far. And then we do the measurement. And as output, we'll get index of elements that we were looking for. In our example for testman, it could be element number 011. And so this is our outcome. So then we get the index of element. And of course, we can check classically whether the element that we have found is what we need to. So yeah, we know how to do measurement. We know how to apply Hadamard to our qubits that are initially in state 0. What remains is the sequence of queries and diffusion transformations. So we need to learn how to implement query and diffusion. So here will be some information. Query operation. We speak currently in terms of function. So suppose that we have function that has n bits as input and 1 bit as output with the following properties. So that if element is marked, value of the function will be equal to 1. If element is not marked, then it will be equal to 0. So Grover's algorithm will not actually search list of elements, but given function f with these properties, which exactly corresponds to finding the element, it finds the elements x for which f of x is equal to 1. So if we consider the following function, which element is marked and how many queries do we need to find the marked element in worst case? So here we see we have 4 elements. And in this example, please tell me which element is marked if we have such function, which is defined for all 4 input values. So which element is marked? Please write in the chat. Element number 4, or if we look at it at the basis states, you can see in this diagram we have elements 0, 0, 0, 1. So which one of them? Yes, thank you. This is the right answer. So we see, if we pass to function element 1, 1, output will be 1, which corresponds to marked element. Function f is often called as oracle. So we can pass to it input like 1, 1, and as output we'll get 1, which says that it is marked element. So even though function is not reversible, it can be implemented in reversible way by the following idea. So we have some additional qubit y here, to which we would apply C0 controlled by fx, basically. So if we have first qubits in state x and last qubit in state y, and especially if it is just state 0, then we'll get just f of x as our output. So this is how we get the computed value function f in reversible way. How to flip the sign? Here we will use the phase kickback effect. You remember we have been checking such notebook, and a reminder is that phase kickback works well if we try to control qubit in state minus. To get state minus, we need to have state 0, apply X gate, and then Hadamard gate. And so here we see if we have put here in state Y state minus, so we apply our query transformation to state where X is our input with which we are working, and minus state to which we will apply our outcome of the oracle. So by doing mathematical analysis here, we conclude that value of state x, because of phase kickback, will be multiplied by -1 to the power of fx. In other words, if fx is equal to 1, then state x amplitude will be multiplied by -1. If fx is 0, then amplitude for state x will not be changed. So as we see here, when fx is equal to 1, -1 is kicked back in front of the first register. So therefore, we need just to have this qubit that awaits our oracle in minus state. So suppose that we have n elements and we have some query operator. What we need to do, we need to prepare qubit to state minus, apply query transformation, and then back return it to initial state. And this is how we will get our query acting. So here we have some hidden function in this task 2. And so this UF is our hidden function. Then we apply operators before and after to have this phase kickback happen. And you can see that at the end we get the following matrix, which corresponds to our query transformation, where element 1, 1 is marked, because here we have multiplication by -1. So we know that in general, we will not be able to pick at the matrix corresponding to the query operator. So in single query, it wouldn't be possible to find the marked element. But this is just to show that indeed, if we have query available to us by implementing the circuit, we would get matrix acting exactly as we need. So our next task would be just to use this operator in our Grover search iterations. Interestingly here, by the way, we can notice that we have this lecture, I guess, divided in parts. Yes, these are two different videos. Inversion operator, as I mentioned, it can be implemented without any oracles, without any knowledge about which element is marked, because all we need to do is just to implement specific operator to do inversion about the mean values. And here is instruction how to implement it. So you need to have ancilla for phase kickback again. Then you need to apply Hadamard X gates, C0 operator, then additional X gate to ancilla qubit, X and Hadamards, and then set ancilla back. So this is a sequence of operators that you need to perform. And here is optional explanation why these operators lead to diffusion transformation. So you can check it in your spare time if you're curious. Currently, just keep in mind that by following the sequence of operations that was mentioned, you'll be able to get the diffusion operator, and this is example for n equal to 4. So diffusion transformation can be implemented just if you follow these instructions. So you can see basically also the same is for Oracle query if we imitate it. All operations that we need are X gates, Hadamard gates, and multiple controlled CNOT operator. So just 3 types of gates cover all the possibilities to implement the Grover search. And as somebody asked in the beginning, when we were tackling real valued qubits, as you see, indeed, for Grover search, it is enough just to have real valued qubits and only real qubit gates. So here, this is code that accepts previously implemented code here. This is why I'm getting errors. But basically, I will just shortly show this is how it looks exactly if you follow the instructions. So we can try to test the Grover search. So suppose we have 4 elements in the list and try to find the marked element. We are given our query operator UF. So we need first to run this cell in order for it to work. And now we need to implement the Grover search itself. We'll need to use some from our previous codes. So this time I will allow myself to show you the solution. So here we launch the code that allows us to load operator UF. We need to apply Hadamards. We need to prepare Ancilla. Then for some number of iterations, we'll repeat query here and inversion operator. And then we send Ancilla back to initial state, do the measurement. So what do we get? So this is a circuit that has been generated, including our query transformation. And what we notice that after one iteration of Grover search, among 4 elements, we have found marked element with probability 1. State 1,1 has been observed 10,000 times out of 10,000. If we have more iterations, then of course our outcome will be different. So with 2 iterations, we see we have each element with equal probability. If we do 3 iterations, then probably again we'll find our element. No, it is not the case. So then 4 iterations. Yeah. So basically, this is the Grover search. So we have Ancilla qubit, which at the end should be returned to initial state. We apply Hadamards at the beginning. Then we use our query transformation here. We use inversion that we have implemented, and we do measurement at the end. And this is a Grover search implementation, how it looks. This is task for a larger number of qubits. So if we use only Toffoli gates, you would need 1 more qubit to implement control by 3 qubits. And then here you're asked to implement this operator, which is inversion operator for larger number of qubits, for 3 qubits, or in other words, 8 elements. So here you can test out on 8 elements. So again, we have more elements. So we have 3 qubits instead of 2. We use 5 qubits because we have 2 ancillas. And the task is to see which state you observe the most. So it is similar to previous task, to task number 3 here, 4, sorry. But this time it will be for a larger number of elements. So if you implemented in task 5 inversion operator correctly, then you would be able to also launch this test. Task 7 is to verify what is the optimal number of iterations to perform. So let's do this together. It is optional, so probably some of you will skip it anyway, but it will be about confirming that indeed our code works correspondingly to our analysis of number of iterations needed. So let's see how it looks. How many qubits we have? We have 19 qubits, but we know that we will work with 10 qubits as our search space, and remaining qubits are our ancilla qubits to compensate the control operations and also this minus state qubit. So basically, our search space consists of 10 qubits. So if we have 10 qubits, how many elements do we have? So this is the first question. Okay, so we have 1024 elements. And suppose that we have only one marked element. We have one marked element. How many Grover iterations is optimal? So what is the number of iterations that is optimal? Please remember the previous notebook where we analyzed with square root of n multiplied by some numbers. So please think about it and write your ideas, and then we will test it. 8 times pi. Okay, so square root of n is 32. And so we have 32 divided by 4, so we have 8 times pi. So 8 times pi is close to 25, right? All right, thank you. So let's see. Here is example where we don't have any Grover iteration, so 0. What we observe more or less each of the states with equal probability. We have very different numbers, but overall, we launch it for 100,000 times. We have 1,000 elements, so roughly 100 for each. Of course, it's a bit fluctuating because it is all probabilistic statistical outcome. So now let's try 25 iterations. This was a proposal. It will take a bit time because simulation. And here you can see that we have found one element with very high probability, 99.9%. And all others, we can see barely 1 or 2 times. So congratulations, your proposal was very correct. 25 was optimal. And just let's see what happens if we have 24. Again, result is very good, but this time it will be worse. We have now probability 99.8. Still very good probability. If we have 26 iterations, 99.2%. By the way, you can see that 26 was closer than 24 because 8 times pi will be 25 point something, which is closer to 26 than 24. So you can see indeed our observations are very closely related to what we have seen in our calculations. Now suppose that we have two market. And by the way, if you have non-optimal number, for example 10, you will still get much better probability for these elements than to any other. And let me find it. So here, for example, you can see 37% probability. Okay, proposal is 20 because we need to divide this number 25 by square root of 2. And 20 is the closest number. Do all participants agree? So basically here with 47% probability, we found one element and 47% probability other. Total probability is 94%, which is quite good. Let's just test 21 and 19. So first 19, maybe it will be a bit better. Okay, 19 is a bit better because probably okay. Or let's be totally clear, will be 8 times pi divided by square root of 2. So this is actually the optimal number, so optimal number should be 18. And let's see, here we tried 19, it was better than 20. And if we try 18, whether it will be even better. And yes, we see 49.9% for each of them. So yeah, you can see indeed this mathematical precision works very well in Grover search implementation. So as I mentioned, Oracle function is something that is hard to implement, and in specific cases, it will just depend on the problem that they are solving. And we can model many different problems as a search problem. So where you have multiple different solutions and you want to find the correct one. Elements in our search space then correspond to quantum states that we have seen, like 0, 0, 0, 1, and so on. Instead of searching the whole space, we can design a function so that it checks whether element is a solution. And then it marks it by outputting 1. So this is why we use word marked. We just mark it like telling that it is what we are looking for. And then we use Grover search to find the solution. We can imitate simple oracle which marks element known in advance. So if we have n equal to 4 and we have element 1, 1 being marked. So solution should be 1 if all qubits are in state 1. And how it can be accomplished? It can be accomplished just by CC not operator, Toffoli gate. So this is our oracle that mimics oracle for state 1, 1. Another example, if we want state 0, 1, then this is how it looks. We need to apply X gate before and after so that now this minus migrates to different state. So basically, adding to CC not operator X gates, you can change which element is marked if you imitate such oracle. So here is a task now to implement your own oracle. Sadly, here it is oracle where you know in advance which element is marked. In Nickel course, you will design oracle which also solves the actual problem. But yes, here is like implementing oracle for specific marked state and then run the Grover search for this algorithm. And task 9 is extra where you have larger example. Those of you who want to see more about Grover search, including implementation, you can see this post. But basically, this is what we have prepared to you in this course. So you both learned how to access Oracle if we have access to it. And here also how to imitate Oracle for specific marked element. We learned how to do diffusion transformation, and we have seen overall Grover search procedure, how to implement it. And basically this finalizes the Grover search. I definitely recommend you now after the lecture to go slower through the tasks of the notebook, which will greatly deepen your understanding. And please don't hesitate to ask questions in Discord. And also, please ask any questions if you have them now. And after that, I will launch the last quiz. So it is question time. Yeah, probably it was much information, so it could be the case that you don't know what to start with. But yes, this whole 3 notebooks summarizes the Grover search. I remind you also that today is the deadline for homework number 2. So if you didn't do it, please finish today. And you will have 1 week to finish remaining 2 homeworks. So basically it means that you have 1 more week to work with the materials to clarify the topic. And also you can ask us questions on Discord. Why divided by 4 to optimal number of iterations? So let's look at this number. And now I will give you some explanation. It is actually, there is a proof why it is so. I'm not sure if I will be able to do it smoothly. I currently didn't have mice or better drawing. So this is our unit circle. We are in some state at the beginning. And here we start as our input state. So basically the best picture would be here. So if we have 1 marked element, you remember from previous explanations, our amplitude will be 1 divided by square root of n. The next explanation is that theta is almost equal to sine of theta for small angles. So when we have many elements, sine of theta, which is our amplitude for marked element, will be equal to theta. Therefore, our initial angle at the beginning is 1 divided by square root of n. So this is where we get this divided by square root of n. So 1 divided by square root of n is theta. And in each iteration of Grover search, our rotation is performed by 2 theta. So therefore, what we get? 1 rotation is equal to 2 times theta. We want to rotate by pi divided by 2. Why pi divided by 2? Because you see, when n is large, theta is small, then this distance is almost equal to pi divided by 2. This is how much we need to rotate. And each rotation is by 2 theta. And what we know that theta is equal 1 divided by square root of n. So let's put all together. 1 rotation is 2 divided by square root of n. We need to rotate total pi divided by 2. How many rotations do we need to perform? We divide just the total rotation by the smaller rotation. So this is how we get how many rotations do we need. So pi divided by 2, the total amount, divided by amount of each of the rotations. So we get divided by 2 square root of n. And so we'll get pi multiplied by square root of n, because you see, you divide by number where it is divided. And this all is divided by 4, because we have 2 here and 2 here. This is where this estimate comes from. On the whiteboard, of course, I would show it in a bit smoother way. Here I needed to switch between screens to make it smooth. But yes, this is how we obtain. Yes, and it's good if you will have questions after playing the materials. All right, I guess I will. Yes, you're welcome. I'm glad. I will switch to the quiz. In 2 minutes, we will do last quiz. And so I will switch my screen to the quiz. And then I will launch the quiz for you. And after that, I will conclude the final session. So here we are. It's the quiz channel. Okay, I will launch it now. Yes, everyone is ready. So let's start. 5 seconds. Here we go. You need to press the button, so please press button number 1. Okay, I see you did it. This time only 11 people participate. Okay. The system that has been updated before, it looked a bit different, but it's always was just clicking the button of correct answer. Well, I see some of your questions have been accepted, but maybe some clicks didn't work. It is strange, like for example, if I click it, then there's no way to tell whether I clicked it appropriately. Let's see whether we'll have new winners this time. All right. So we have new winner today, just 11-point difference. I have too many screens to click. All right, then that's it for the lecture and for quizzes. The first 2 places also, according to number of points, all had correct answers, which is also a good sign. Yes, we'll definitely need time to go through materials once more, and maybe in slower pace, but it's totally fine. And some parts of implementation are even considered as optional part of the notebooks. So if you master to implement it, then it is a fantastic job from your side. I have reminded you about the homework, and also I remind you about one more meeting that will happen today here. So at 6 o'clock, there will be one more meeting. So please join it. It will be after 2 hours.